Okay, in part one of the example, we parameterized our surface, which was our cylinder, and then we found RU cross RV was this, and this was our F. So in part one, we showed that the flux of the curl across S was 0. So in this video, to verify Stokes' theorem, we're going to have to show that the line integral around the boundary is also 0. So the boundary here, there's actually two boundaries. You have one up here and one down here. So the C here has to be taken in the positive orientation. So we'd have to figure out the which way the normal vectors are pointing. This is the normal vector here, and that'd be kind of tricky. So I'm not going to try and work that out. I'm going to draw my D region and take it in the counterclockwise direction, then map it onto R to get the correct orientation over here. Okay, so let's do that. So here's my D region. So it's 0 to 2 pi on the U, 0 to 4 on the V. And now I'm going to take it like in Green's theorem, going in the counterclockwise orientation or direction around the boundary of D here. And then I'm going to map it under R to find the correct orientation for the boundary of S. So again, the boundary of S actually has two. It has a boundary up here and has one down here. So we have two guys to worry about. So let's first parameterize C1 tilde. Okay, I'm going to call it R1 tilde. So parameterizing C1 tilde, calling it R1 tilde. So the start point 0, 0 plus end point 2 pi 0 minus start point. So times t. Working this out, you get 2 pi t 0. Okay, now let's map it under R and call it R1. Okay, let's do that. Okay, so I'm going to call R1 then R composite R1 tilde of t. Okay, and it's going to, so R1 tilde of t is 2 pi t 0. So I'm going to go up to my R up here. In place of U, put 2 pi plus t, so here and here. In place of V, put 0. So doing that, we get this then. So again, putting 2 pi t in place of U here and here, and 0 in place of V. So that's going to be on the lower one, it looks like, because the Z component is 0. Let's see where we're at time 0. So let's stick 0 in place of t, and 1 in place of t also. So plugging 0 in, we'll have then, in place of t, we'll have 2 cosine 0, 2 sine 0, comma 0. Cosine of 0 is 1, so it's going to be 2, 0, 0. Okay, so if I graph that up here, let me put in my x and y axis. So I put in my x and y axis, so then 2, 0, 0, 2, 0, 0, yeah, so it'll be right here. Let's actually do, say, instead of, say, 1, let's do 1/2 for t. Sorry, not about 1/2, 1/4, say, for t. So putting 1/4 in, you'll have then, in place of t up here, 2 cosine pi over 2, 2 sine pi over 2, 0. Cosine of pi over 2 is 0, sine pi over 2 is 1, so it'd be 0, 2, 0, so it'd put you up here. Okay, so now I can draw on the orientation. So let me do that. Okay, so I've drawn the orientation here. Okay, let's keep going now. Let's find R2 tilde next. Okay, so doing R2 tilde next, that's the parameterization of C2 tilde. So starting point would be 2 pi 0. Ending point would be here, which would be 2 pi comma 4 minus start point times t. So working this out, you get 2 pi comma 4t. Okay, now let's map it under R and call it R2. So we'll get this then. So R2 is defined to be R of R2 tilde, which would be R of 2 pi 4t from up here. So I'm going to put 2 pi in place of U, 4t in place of V in up here in my R guy up here. So let me do that. So I get this then. So again, putting 2 pi in place of U here, putting 4t in place of V here. we'll get this. And the cosine of 2 pi is 1, so this will be 2 here. Sine of 2 pi is 0, so it'll be 0 here, 4t. At time 0, if you put 0 in there, you'll see it'll be at 2, 0, 0, so it'll be here. And you put 1 in there, you'll be at 2, 0, 4, so here. So it's actually going up like this. Okay, now let's parameterize R3 tilde next. Let's call it, sorry, C3 tilde, let's call it R3 tilde. Okay, so parameterizing C3 tilde, let's call it R3 tilde. So it's start point, so you're starting here, which is at that point would be 2 pi comma 4, plus ending at this point over here, which would be 0, 4, then minus start point, t. Working that out, you can check it's pulling a 2 pi out there, it'll be 2 pi times 1 minus t comma 4. Now let's map it onto R and call it R3. So let's do that next. So calling it R3, it's going to be R of R3 tilde, it's going to be R of 2 pi times 1 minus t comma 4. So that's my U, that's my V, up in my R up here. So putting this guy in place of U here and here, 4 in place of V here. So let's write it over here. So plugging in, you get this then. Okay, so that's actually going to be the top circle up here, going around it. But the 1 minus t, if you compare it with the R1 up here, you just add 2 pi t here and here, and a 0 is putting us on the bottom circle down here. The 4 here puts us at the top one. But the 1 minus t is going to reverse the orientation from this one. So I'll let you check. The orientation will be reversed. So let me draw that in up here. So I've drawn it in up here. Let me call this one C1, let me call this one C2, and let me call this one C3. Okay, so I've labeled C1, C2, and C3 here. Okay, let's do the last one now. Let's parameterize C4 tilde. Let's call it R4 tilde. Okay, so I put my R3 guy up here. So R4 tilde now would be start points would be 0, 4 plus end point 0, 0 minus start point. So working that out, the 0 here. And you have 4 here and here. I'm going to pull a 4 out. It'll be then 1 minus t in there. Now let's map this under R and call it R4. So R4 then will be R composed with R4 tilde. R4 tilde is 0, 4, 1 minus t, so it'll be R of 0, comma 4, 1 minus t. That's going to be my U value. My V value up here in my R. So let me write out what you get here. So putting 0 in place of U here and here, you have 2 cosine 0, sine 0, and 4 times 1 minus t in place of V. Okay, so cosine of 0 is 1, so it'll be 2 here. Sine of 0 is 0, so it'll be 0 there. So we write it out here. So you get this. And notice at time 0, if you put 0 in place of t here, it'd be at 2, 0, 4, so it'd be starting here. And if you put 1 in place of t, it'd be at 2, 0, 0, so it'd be down here. So it'd actually be coming down this way. So let me draw it in. So it's basically just R2 with the orientation reversed. So they'll actually cancel each other. So we'll talk about that in a second. So we've got everything we need now. So these two, C2 and C4 will cancel. Okay, so let me erase some things now. Oh, well, before I erase things, let me just mention, you might say, well, the one down here is going in the opposite orientation of the one up here. Will they cancel? And the answer is no, because they're in different locations. See, this one's going up and one's coming down over the same curve. Here you have a circle on the bottom, bottom here, and a circle on the top up here, this way. They do have opposite orientations, that's true, but they're in different locations, so they won't necessarily cancel. In this case, actually, they have to cancel because you know the answer has to be 0, but in general, that will not be the case. Okay, so let's keep going. So we'll have this. So the line integral over C will equal to 1 over C1 plus C2 plus C3 plus C4. Now, as I mentioned already, I erased the picture, but the R2 guy and the R4 were just opposite orientations of the same path. So actually these two, so 2 and 4 will cancel. So it'll just equal then C1 and C3. Okay, so it's just going to be C1 and C3. So let's start doing these now. Let's do C1 first. Okay, I can erase now my R2 and R4. So I'm just going to leave my R1 and R3 up there. Okay, so to do the line integrals, I'm going to have to find R1 prime and R3 prime. So let me write R1 prime here first. So taking the derivative of R1 prime, so derivative of cosine would be minus sine, but then you have to do derivative of the inside, which would be 2 pi, and 2 pi times 2 is 4 pi, so that'll be minus 4 pi sine 2 pi t. Then derivative of sine is cosine, derivative of the inside would be 2 pi, so 2 pi times 2 would be 4 pi, so it'd be 4 pi cosine 2 pi t, 0. Okay, and now let's start doing the line integral. Okay, doing integral over C1, here's the definition. The t is going to go from 0 to 1, by the way, we parameterize the line. Parameterize our R1, sorry. So it's going to be this guy here. So, and here also, from R1 prime, I pulled out a 4 pi just to make it easier to write. Here's my f up here. So in place of x, I'll be using 2 cosine 2 pi t. In place of y, I'll be using 2 sine 2 pi t. In place of 0, I'm going to put a 0. So plugging into this guy here. So let's write it here. So plugging in, we get this. So again, I'm plugging into this. So it'll be I x, but x here is 2 cosine 2 pi t j, then y times z, but z is 0. Just going to make this one a 0. Then I have my R1 prime here. Put down here. So dotting these, it'll be this guy with 1 here, cosine with cosine, 0 with 0. So let me write that over here. So dotting, we get this. I pull the 4 pi out in front here. That'll be minus sine here, and cosine times 2 cosine will be 2 cosine squared. Now I'm integrating cosine squared, so I'm going to have to make a substitution here. Actually, before doing that, let me make another substitution just to make it a bit easier. Let's let u equal 2 pi t. So I'm going to let u equal 2 pi t, then du dt would be 2 pi, then du would be 2 pi dt. And I can notice here, I can bring a 2 pi inside here. Let me do that. So in particular, I'm just going to leave a 2 outside there and bring a 2 pi and put it beside the dt just to make it easier here. Okay, so I've done that. So I have a 2 pi here and a 2 outside there. It's still 4 pi. So making the u substitution then. We get this then after making the u substitution. And then a u of 1, so put 1 in place of t, or this would be 2 pi up here. 0 in place of t here would be 0. Okay, so now we're going to have to do a double angle on the cosine squared here, so let's do that. Okay, so we're going to replace the cosine squared with 1 plus cosine 2u over 2. These two will actually cancel in. Oops. Okay, so let's rewrite it now. So we get this then. Then let's integrate these guys. Let's do that. So integrating, we get this. So integral of minus sine would be cosine. Integral of cosine 2 theta would be sine 2 theta divided by 2. Integral of 1 would be u. So when you put in 2 pi and 0 into these trig functions, actually, they're actually going to become 0. You just have a 2 pi times 2. I'll let you check. It'll be 2 pi. Sorry, 2 times 2 pi. So we'll get 4 pi from this guy. Okay, so that's integral over c1 is 4 pi. So the integral over c3 better be negative 4 pi, because we know the final result should end up being 0. So let's check that. Okay, so let's first find R3 prime. Okay, so R3 prime, so it'll be derivative of cosine, which would be minus sine, times derivative of the inside with respect to t would be minus 2 pi. So you'd have two minus signs would be a plus, and you'd have a 2 pi times 2, so 4 pi sine of this guy. Derivative of sine would be cosine. Derivative of the inside would be negative 2 pi, so it would be negative 2 pi times this, negative 4 pi cosine, and derivative for 0. Okay, so let's do this the line integral now over C3. Okay, so I'm going to plug into my f up here, but this time my x will be the 2 cosine 2 pi 1 minus t, my y will be 2 sine 2 pi 1 minus t, and my z will be 4. So then I'll be dealing with this guy here, so let me write that down here. So I get this, so again it will be I x, but x now is 2 cosine 2 pi 1 minus t here, plus yz. Y is 2 sine guy, the z is 4, so it'll be 4 times 2, so it'll be 8 sine 2 pi 1 minus tk. Then dot it with our R3 prime. I pull a 4 pi out here out of this guy, so it'll be then sine I direction minus cosine j and 0k. Alright, so let's dot these now. And I'm going to pull the 4 pi out when I dot also. So dotting, we get this. So I pull the 4 pi out, then I'll have the sine times 1. I'll have the minus cosine guy times the 2 cosine 1 here. So I'll have minus 2 cosine squared, and then 0 times this. Okay, I'm going to make a u substitution again. And I'm going to let u equal this guy. So 2 pi times 1 minus t. So I'm going to let u equal 2 pi times 1 minus t, then du dt would be minus 2 pi, so du then would be minus 2 pi dt. Okay, I'm going to take this 4 pi and put a negative 2 pi here, and then put a negative 2 outside here in place of the 4 pi, so let me do it. Okay, so now I rewrote the 4 pi as, well, you can check if you go negative 2 times negative 2 pi here, it'd be 4 pi. So I just wrote it like this to make the substitution easier. Okay, let's make the substitution now. So making the substitution, we get then sine of u minus 2 cosine u squared, and that right there becomes my du. And u of 1, so if you put 1 in place of t here, that'd be 0. And if you put 0 in place of t here, you'd end up with 2 pi. So we can then change the order of this around, and we'll introduce a minus sign, and we can cross it off with that one. So let's rewrite it over here. So we get this. We could then integrate this, but let me just pull a minus sign out here and talk about something for a second. So let me just factor a minus sign out. So factoring in a minus 2, we ended up with this. But if you notice here, if you go back and check, you could integrate it, it's not that hard to integrate, but if you just notice here that that integrand is actually the same as the one we got when we did C1, but we had a 2 out there when we did the C1, now we've got a minus 2 out here. So pretty much it's going to be the same answer with a minus sign, so therefore it's going to be minus 4 pi. You could go through and just show it making the double angle substitution and stuff like that, but you line up at negative 4 pi. Okay, so now let's add our results together. Hence we can conclude then that the integral over our boundary equals integral over C1 plus integral over C3, which is 4 pi for the C1 guy minus 4 pi for the C3, which is 0. So this verifies Stokes' theorem, because in part 1 we showed that the double integral over the surface was also 0 of the curl. So we're done. Just to be explicit, so we've shown this. Okay, so we're done.